Good morning, students. Today we will discuss about the state space representation of models which correspond to the unit number 2, in which the system analysis method can be classified into two terms. That means the first one is the classical method or transfer function based method, and second one is the state variable method. As we have seen that in the transfer function based method we can enlist some of the points, just like the for by using the root locus, polar plot, mode plot, and the Nyquist plot. In the number unit 4 we already read about the root locus. Now the remaining portion of this one, just like the polar plot, Bode plot, and the Nyquist plots, we will discuss about in the unit number 5. Okay. So there is a large differentiation between the classical method and state variable method, because in the classical method, which is generally used for the transfer function based method, in this method there are some limitation, just like it can be used only for the linear time invariant system, and the major drawback is that in the transfer function based approach, the initial conditions must be zero, because we know that the definition of the transfer function, it is a ratio of the output transform to the input transform with assume all initial condition is zero. But in the state variable approach, initial values cannot be always zero. We have to assume zero, but it's not always zero. Yeah, clear. That means initial values are given, but in the transfer function the initial values always to be zero. So there are some limitation of the classical method, just like first one I have described. For it can be used only for the LTI system, linear time invariant system. That means is not applicable for the, or we can say the limited application for the non-linear system. But generally we can say that it is only used for the LTI, linear time invariant system. The second one is the classical method is only method for single input single output system. Third point is the this method do not describe the internal state of the system, that means the initial values of the system. Number 4 is the this method gives only zero state response which is based on input. Now comes with the plus point, that is the advantage of the state space approach. Okay, now comes with the advantages of this method, that means the state variable method. We have to, what is the plus point about the state variable approach? So first one is the, as I know that it can be valid for linear, non-linear, time variant, and time invariant system. That means approximately all types of the system can be used in the state space approach. And the second point is the it can be applicable in the both type of systems, such as that means in single input single output system, and also for the multiple input multiple output system. Now third point, which is a basic, very important, that I also discussed in this method, the internal state of the system is described. That means the initial values of the system is described, assume. Now comes with the number point 4. This method provides both zero input response and zero state response. Number point 5 is the, as the method involves matrix algebra, can be easily adopted for the digital computer, that is a state space analysis can be easily programmed, and hence suitable for analysis using modern computer methods and techniques. Now after some few plus point, we have to represent the state variable method. That means the mathematical approach is just started by using the state variable method, so in which we have assumed that some variable, just like the x dot is equal to ax plus bu and y is equal to cx plus du. Here y indicated the output response and x dot equation indicated the generally the input response with the dynamic equation, we can say that overall. So now comes with the all these parameters which we have discussed in the lecture. U is the m cross 1, that is the column matrix, and A is the n cross n, which is the square matrix, and B is also a square matrix. Now in the classroom we have defined all these terms, just like the state, what is the state, state variable, state vector, state space. So after that comes with that directly into the numerical portion, which is the representation of the differential network. How we can represent a differential network by using the state space approach. So this is the basic very it's a basic example to show about the how the second order differential equation can be represented by using a state space approach. So we are here we are using only a second order differential equation. So as we have seen from this equation, a into second order xt plus b d upon dt xt plus c xt is equal to ut. Here a b c is the coefficient and ut is the scalar vector. Okay. Now comes with the initial values. As in this question we given as d upon dt xt is equal to 0, x of t is equal to 0 at t is equal to 0. That means these are our initial values which we have given. Now comes with the solution. So according to the solution, here we are using a second order differential equation. That means the number of order is 2. So the total state variable will be 2. Now in such type of question we have to assume that the x of t is equal to x1t and its derivative d upon dt xt is equal to x2t. It can be represented by x1 dot t. So write the above equation, which is the second order, by using these assumptions. So we will get a x2 dot t plus b x2 t plus c xt, or you can say that c x1 t is equal to ut. Now solve this equation, or you can say that rearrange the equation for x2 dot t. Now x2 dot t in the left hand side and all the remaining terms in the right hand side. So we have obtained two equations. First is the x1 dot t is equal to x2 t, which we have already assumed. Now second equation we solve for x2 dot t. Now write in a matrix form by using two equations. So x1 dot t and x2 t in a column vector, in a row vector, it can be represented by 0 1 minus c by a minus b by a into x1 t x2 t plus 0 1 upon a into ut. 0 because in the x1 dot t equation we do not have any ut term, but in the equation number 2 x2 t we have a term 1 upon a, which is the factor of ut. Now overall we can represent a block diagram. Just it's showing the block diagram representation of the state model. Equation number 2, that is the x2 dot t, fully expressed by using the block diagram representation. Okay, that is the portion of the differential network. Now comes with the electrical network. The second model which is showing in the sheet is the electrical network. Okay, so it's a very simple network in which only R, L, C component are present, where we are using the VL, it's the voltage across inductor, VC is the voltage across capacitor, flowing current is the IL, and applying input voltage is the VS, and here resistance R. So apply only simple KVL in this electrical network. Okay, so equation number 1 is find out. So after that solve this one for di upon dt. Clear? Now also we can find out IL is equal to C into dVc upon dt, that is the current across the capacitor. So solve for dIL upon dt and dVct upon dt, and after that rearrange in a matrix form. The equation can be represented in a matrix form. Now second example also showing a electrical network which having the two node voltage, as we have seen that V1C and VC2. Okay, as in some books we are represented V1 voltage and V2 voltage. These are exactly node voltage, so we have to apply a KCL in V1 and V2 node. Okay, so firstly apply KCL at node V1. So we obtain equation number 1. Apply KCL at node 2, that is the V2. So we have to find out equation number 2. Now equation number 3 can we find out the flowing current, that is IL across the inductor. So we have to find out the voltage across inductor. So equation number 3 is represented the voltage across in the a current across inductor. Okay, so IL is the flowing current across inductor. So equation number 3 represent the total flowing current across inductor. Clear? Now rearrange these three equations as in the previous method. So we have to find out these three modified equation, that is the equation number again dvct upon dt, di upon dt and dvc2 upon dt. So arrange these three state variables in a matrix form. That is the final answer for the using state space approach in a electrical network. Thank you.